I'm going to work problem number 6 out of this book. It's on page 329. And I think it's a rather simple problem. It says a 12-pound body attached to a helical spring stretches it by 6 inches. After it comes to rest, it is stretched an additional 4 inches, then released. Find the equation of motion of the body, also the period, frequency, and amplitude of the motion. With what velocity will it cross the equilibrium position? Okay, very simple problem. It does not take into account the frictional characteristics of the spring. All right, so we attach a 12 pounds to this body and stretches it 6 inches. Now, weight is 12 pounds. And by the way, what's the mass? We have mass times acceleration. Gravitational acceleration is 32 feet per second squared. And so if we divide by all this mess, divide by 32, we get the mass. So 12 over 32, which is, what is that, 3 eighths? 3 eighths. And it's pound seconds squared per foot. Okay, pound seconds squared per foot is the mass. Well, in this system, we call, the English system, we call that mass slugs. So that's equal to 3 eighths of a slug. All right, well, you don't encounter that much these days because when you take physics, almost all physics anymore is done in the metric system. So we don't see slugs. But this is kind of an old book. Some of the problems are done in English system. So I thought it was worth looking at slug. But I don't really need that because the weight, mass times gravitation, is already 12 pounds, and that's k times the stretch length. So let's go back to this part, and we'll figure out what k is for our problem. A 12-pound body attached to a helical spring stretches it by 6 inches. So this is 12 pounds. Weight, mass times gravity, is 12 pounds equals to k times 6 inches. Now 6 inches is 1/2 foot. So here's a very important comment. Don't work in inches because gravitational acceleration is measured in feet and also in seconds, second squareds. But because it's measured in feet, we need to keep and stay in feet. And weight is measured in pounds normally. So let's, unless you're willing to change your gravitational acceleration units, if you're going to stick with 32 feet per second squared for g, then we need to be working in feet and pounds. So multiply and divide here. This is 24 pounds per foot. It's equal to k. So if you're wondering what the units of k are, they're weight per distance, weight per distance, or force per distance. In other words, every foot requires 24 pounds. So to stretch it 1 foot, you got to exert 24 pounds. 2 feet would require 48 pounds. So forth and so on. So anyway, k is equal to 24 here. I'm not going to worry about the units, but it's worth looking at. But anyway, k is equal to 24, and length was equal to 1/2 foot, not 6 inches. Well, 6 inches is 1/2 foot, isn't it? All right. Well, but do I really need k here? Well, if I wanted k, I now have it. So, but the way I've got this set up, I've got g over L. So maybe I don't need it. When I plug the numbers in, y double prime plus 32, g is 32, because we're working in the English system, English units. Length is 1/2 times y equals to 0. Then y double prime plus 64y equals to 0. There we go. And when we solve, or actually we could just really write in the answer here if we wanted to. We have pretty much it figured out. But we can solve this. M squared plus 64 equals to 0. The roots of the characteristic equation are plus or minus 8i. And that would give us solutions we could write out. So y of t will equal to c times cosine, and square root of g over L is the square root of 64. That would be 8, so it would be 8t plus delta. Or we could write it as y of t is c sine 8t plus delta. There we go. We have a choice. And what choice would you use? Well, let's look at the problem. After it comes to rest, it is stretched by an additional 4 inches and released. Alright, so I didn't really write up the full problem, did I? So let me kind of separate this off. Here's our differential equation, but the initial position is 4 inches beyond equilibrium, plus 4. So we stretch it down a positive 4 inches, which is 1/3 of a foot. So the initial position is 1/3, and then the initial velocity is going to be 0 because we just let it go. We don't tap it down further, we don't throw it upward. So first derivative is 0. So here's our full differential equation describing this problem. Y double prime plus 64y equals 0. Y at 0 equals 1/3. Y prime at 0 equals to 0. So initial velocity is 0. Initial position is 1/3. Which of these do we want to use? Let's use cosine. All right, for a very good reason. Because cosine, without a phase shift, just y equals cosine of x. Looks like this. So cosine of 0 is 1. It starts at the top of the curve. And if my initial position is 1/3, it's up here, then I want to use a cosine because it starts up here somewhere. Now, if I had a sine function, y equals sine x, without any phase shift, starts at the origin. And so if the initial position was 0, but it had an initial velocity, then I would use a sine because initial position is 0. So I might make a note here. For initial position at 0, you're going to be better off using sine. I think it's going to simplify this issue with the phase angle. If your initial position is non-zero, then you want to start off with cosine. So let's see if that worked out nicely here. So one more time, I chose cosine because my initial position was non-zero. So I have this solution, y of t is constant c cosine 8t plus delta. Now there are two constants here that we have to solve for, and that makes sense because it began as a second order differential equation, so we expect two constants. And I'm going to need the derivative. So y prime of t will be, let's see, it's going to be minus 8c sine, parentheses 8t plus delta. So derivative cosine is minus sine, chain rule, we have to multiply by 8. Alright, so let's plug our initial conditions in. Y at 0 will be c cosine delta. That equals to 1/3. And y prime at 0 is equal to, minus 8c minus 8c sine delta. That equals to 0. Now, here's where we get our payoff by choosing cosine, because in this equation, c is non-zero, we're going to assume, because otherwise if c was 0, y would equal to 0. So the only solution is where sine of delta is equal to 0. Well, that makes delta equal to 0. The angle is 0. And by the way, just a reminder, our angles are radian measures, not degree measures. Radian measures. Anyway, so delta is equal to 0, which means that c cosine of 0 equals to 1/3. Well, the cosine of 0 is 1, so c times 1 is c equals to 1/3. So this tells us that the amplitude is 1/3 of a foot, which makes sense. We stretched it by 4 inches, so it bounces up and down 1/3 of a foot either way from equilibrium. And the phase angle is 0 because we chose the cosine function. So I need to write my answer here and then see if I can answer all the book questions. So out of all this mess, we have our solution. Y of t is 1/3 cosine 8t. And that satisfied not only the spring problem, but also the initial conditions. So let's see if we can answer all the book questions that they ask. And the first question is problem number 6. Find the equation of motion of the body. Okay, there's the equation of motion. What's the period, the frequency, and the amplitude? Alright, well the amplitude, this sounds like a trigonometry class question now. Amplitude is 1/3 foot. And the period, you remember how to figure period? It's 2 pi divided by the coefficient, in this case 8. So this is pi over 4. And period is in seconds. So that means in pi over 4 seconds, whatever that works out to be, 3/4 of a second, it does one up and down bounce. So you pull it down, you let go, it goes up, and then comes down. In pi over 4 seconds, that's one period. They also want the frequency, which I think the frequency is a lot more interesting than the period. But the frequency literally is 1 divided by period. So it's 4 over pi seconds, which is 4 over pi hertz. So hertz, named after a 19th century physicist, not the Hertz rent-a-car guys. Hertz studied sound and wave patterns and things like that. So a 1 over a second is a hertz. It's 1 over s, or 1 over a second. And so the frequency is 4 over pi hertz, and which is, I don't know, a little over 1 per second, 1 vibration per second. We had one other question to answer. With what velocity will it cross the equilibrium position? Okay, with what velocity will it cross equilibrium? So the position, where is this position equal to equilibrium? It's where this position equals to 0. And so, in other words, equilibrium is where the position is 0. So solve for t here. Well, cosine of 8t is 0. Cosine 8t would be 0. And where is cosine equal to 0? That's when this part here is equal to either 90 degrees or pi over 2 radians. So we have to work in radians here. So 8t is equal to pi over 2. So think about that on a circle. Sines are x's and cosines are y values. Oh, I got that backwards. Sines are y's and cosines are x values. And so cosine is 0 at the top here, at pi over 2 or 90 degrees? Well, we have to use radians here to get good answers. So at would be pi over 2, which means time would be pi over 16. So what velocity would that be? Well, the velocity is the first derivative. So the first derivative is going to be minus 8/3 sine 8t. And so if I plug that time in there, y prime of t would be minus 8/3 times the sine of 8 times pi over 16 minus 8/3 sine of pi over 2. Okay, well, sine of pi over 2 is equal to 1, isn't it? Equals to minus 8/3. So the maximum velocity is 8/3 feet per second. Now, do we call it minus or positive? Well, going up it's going to be negative, come back down it's going to be positive. So why don't we just say it's 8/3. Alright, well, did I get all those correct? Feeling pretty confident about this one. We have the right equation of motion, y equals 1/3 cosine 8 of t. The period was pi over 4 seconds. The okay, frequency was 4 over pi cycles per second, CPS. By the way, he said this pi over 4 seconds is also 8 radians per second. I'm going to avoid radians as we'll call it pi over 4 radians. And anyway, the frequency is 4 over pi cycles per second, or hertz. Got that right. The amplitude was 1/3 foot. And the velocity, he wrote it as plus or minus 8/3 feet per second. So that's how he dealt with the plus and minus. He just called it plus or minus. Alright, well, it's going to get a little more interesting as we move along here, but this was an example of simple harmonic motion, resulting only in a sine or cosine wave. When we build in the resistance qualities, then it's going to get a little more complicated.